Welcome back, guys, to another video. This time we're determining the normal stress in a rod AB, and we have a loading, and that loading is being applied to this member AD of 50 kilograms. So let's quickly convert that into a weight. So we know the force equals mass times acceleration. The mass is 50, the acceleration is 9.8. That gives us 490 newtons. Okay, so we might approach this problem a bit like the method of joints. If you don't know the method of joints, that's okay. I'll go through it in this video anyway. What we want to do is work our way up this problem so that we get to know the value of the force in this member, AB. Because once we have that force, we can just apply our usual stress formula. So stress equals force over area. But before we do that, we need to know that force, okay? Force of member AB. Okay, so let's start by looking at the joint D. Joint D. Because if we look at joint D, hopefully that'll give us the force in this member, AD, and then we can work our way up and across. So joint D, let's draw the free body diagram. We've got 490 newtons as our applied load, plus we're going to have this member AD. Without doing any sum of the forces, we just know by looking at it, if we've got 490 newtons going down, we're going to have 490 newtons going up. And because it's going away, it's acting away from the joint D, right? We know that's going to be in tension, okay? So we have that value now. We can look at joint A. Let's draw the free body diagram for that joint. So we can draw that load, 490 newtons. Remember, so AD, 490, and that's in tension. So that's always going to remain in tension. So it's acting away from joint D, yeah? That's this load that we just calculated. Then we have this member up here, and then we have another member here that we're interested in, that we're really interested in. Sorry, I made a mistake. That's joint A. That's B, and that's C, okay? So we don't have the angle for this, but we do have 5, 3, 4 values given to us. Let's start by summing the forces in the y, because we have this y load known to us. 0 equals this load, negative 490, plus the y component of AC, the member of AC. We want this y component here, this y component. So the hypotenuse of that triangle will be AC, and we don't know the angle, but we want to know what its relationship is to the sine of that y component. So sine, and we don't know the angle, so we'll just calculate it. That's going to be arc tan, opposite over adjacent, so the opposite is 3 over the adjacent, which is 4, 0. So by rearranging, AC is 490 divided by sine arc tan 3 over 4. Okay, and when I put that in my calculator, I'm getting 816.67 newtons. So we've assumed that this member is going, the force of this member is going up like that. So, and that's acting away from joint A, so that's going to be in tension as well. Okay, so now we have the force of AC. So let's sum of the forces in the X so we can get the AB force that we really want. So that's going to be the X component, well, let's start by negative AB, assuming negative because that's going to, if AC is going up and to the right, this is just going to go, AB is just going to go to the left, isn't it? So negative, negative X direction. So plus, now we want the X component of member AC, don't we? So to do that, we have 816.67 that we just calculated. It's going to be the cosine of arc tan 3/4 equals 0. AB equals 816.67 cosine of arc tan 3/4, and that equals to, if you put that in your calculator, 655 newtons. Okay, and that's acting in tension as well. All right, great. So hard part's done. We have the force. Now to apply our very simple equation. So stress represented by sigma equals force over area. So the force is 655 newtons, and the area is, how are we going to calculate the area? So we know that the area of a cylindrical rod, we assume it's cylindrical because it's a rod, area is equal to pi r squared, isn't it? So this will be, we have the diameter of the rod is 8 millimeters, but the radius will be 4 millimeters, correct? So let's apply that. Area equals pi times the radius. Let's convert the 4 millimeter radius into meters. 0.004 meters squared. That'll give our stress in pascals. Okay, so that gives us, if you pop that into your calculator, that should give you 13 times 10 to the 6 pascals, otherwise known as 13 megapascals. That's the answer.